Hello guys, my name is Dana.
I'm Celeste.
I'm Elena.
And I'm Aida. And we're from Group 71. And this is our first partial project. Our teacher is...
Hello, this is Sarah. How may I help you?
I'd like to invest my money into your bank and an account, please.
Oh, there are many options here. Let me show you.
So the problem says that a man invests initially $6,500 into an account that pays 6% interest per year. So what it's asking us to find is A, find the amount after 2 years if the interest is compounded semi-annually. B, find the amount after 2 years if the interest is compounded continuously. C, graph both models from questions A and B, leaving T as a variable. D, based on the graphs from question C, answer the following. What model, interest compounded semi-annually or continuously, grows faster? And E, based on the graphs and using the tools from the graphing software, approximate how many years must pass so the amount is now $19,500 for both models.
Flowchart. So first, we must read the problem and understand it. Then, we must identify the main exponential function where t is years. Then, we have to substitute t for 2, so that will leave e raised to the 0.6 times 2. And then we solve to get 6,500e raised to 0.12. After that, we raise e to 0.12 and we multiply that times 6,500. And finally, we graph our function with a graphing software.
Semi-annually compounded interest.
So this is the formula we're going to be using. This is for semi-annually compounded interest. And T is the initial investment we make. Which should be 2,500. And then this is the interest you would be paying semi-annually, which is 6%. Then N stands for the number of times you pay this a year, that's 2, and T, the number of years. Yeah, but this is only just one option. I'm going to introduce you to like the implementation of the
Great.
Continuously compounded interest.
Hi, I'm the implementation of the bank and I'm going to explain you the continuously compounded interest. So the formula A of T equals P times P to the RT. P is equal to the initial investment that is equal to 6,500. E is a constant and is equal to 2.72. R is the interest and it's 6% or 0.06. And T is the time of years that in your case is 2.
So in the semi-annually compounded interest, the variables mean the same, but now we're trying to find t, already knowing that our final amount has to be 19,500.
Okay, well, I guess from what I learned from being here and looking how you solve all the problems, for continuously compounded interest, if I wanted my final amount to be 19,500, I would plug in the numbers and leave t as the unknown. And so I would solve it. I would add ln to both sides, and ln e cancels it out. And so my final amount would be 18.31 years. Okay, well, right now we have both graphs side by side. The first graph is the semi-annually compounded interest, and the second graph is the continuously compounded interest.
So then, what model or interest compounded semi-annually or continuously grows faster, and why? Well, the model that grows faster is model B, or the continuously model, due to the fact that it's continuous instead of twice a year. Conclusions.
While doing this project, we learned to apply logarithms to things that actually happen in our lives. With this application, we understood the utility of logarithms in our life.
It really did make us see ways in which we could use logarithms. Logarithms can be used in any situation when you're dealing with numbers, in terms of powers of 10 or numbers with lots of digits.
Real-life applications for this equation include inflation interest rate for stocks, population, seismic scale, and acid and base scale too.
We also learned that exponential functions tend to grow faster than logarithms, and this work was easier because we did it as a team. Thank you.